Hello everyone. Welcome to the lecture 18 in the course Diffusion in Solids. So today we will continue our discussion on the correlation factors. Last class we introduced what is correlation factor and how the structure and the mechanism can influence the correlation factors. Um, Today we will see some ways to calculate the correlation factor. We'll take the example of the cubic lattice, and we'll also see the solute correlation factor. So, uh, we saw the expression for the correlation factor, which is F equal to mean square displacement when you have a correlated walk divided by mean square displacement when you have a random walk, which equals 1 plus 2 by n summation I equal to 1 to n minus 1. Again, summation j is equal to I plus 1 to n, summation of average of cos theta ij. Now, if you expand this inner summation, what you can write is f equal to 1 plus 2 by n summation I equal to n minus I2 equal to 1 to n minus 1 cos theta I plus 1 plus cos theta I plus 2 plus cos theta I plus 3. What does this value mean? For example, cos theta I plus 1 average means that if there are n number of atoms which are making a jump, what is the average of cos theta of all these atoms between the ith and the I plus 1 jump? Suppose for one atom, if the cos theta I plus 1 is plus half. For second atom, it is minus half. For the third atom, it is minus zero point 0.8. For fourth atom, it is minus zero point 0.5. Then what is the average of these all jumps of I plus 1 for all the atoms? Similarly, then it is for cos theta I plus 2. That means ith jump and I plus second jump. Now, for any cubic lattice, we can show that the cos theta I plus j, average of cos theta I plus j, is equal to average of cos theta I plus 1 to the power j. What the relation says is that if you want to evaluate the average of cos theta between ith jump and I plus jth jump, then you can simply evaluate the average of cos theta for I and I plus 1 jump and just raise it to the power j. This is a very important relation which simplifies this expression. But for now, we will try to see if we can prove it at least for a simple cubic lattice. So, let us consider a simple cubic lattice where this A represents the vacancy and you have these different sides. The coordination number is 6 in this case. So, let's say the atom X, it was initially here and it has made its ith jump from A to X. So, this atom X actually was here. It made its ith jump from A to X such that now A is a vacant site and atom is at position X now. So, I write like this, that ith jump has been made from A to X. Now, where will the next jump be? Okay, remember we are talking, we have to consider all the possible jumps and so on, right? So, right now we will try to consider I and I plus 1 jump. So, ith jump, if it is from A to X, where will the next jump be? So, I've drawn this figure again here. Now, the next jump can be in any of these 6 sites which are denoted here. A, B, C, D, E, F. So, all these possible sites, there is a 6 coordination number is there for the simple cubic lattice. So, this atom X can jump to any of these 6 sites. Now, therefore, write these possibilities of I plus 1th jump. Remember, ith jump was from A to X. So, I plus 1th jump can be from X to any of these sites. Now, let us write down all the possible cases. The first case, it jumps back to A. So that means this can come here back to A. This is called as a reverse jump. You can see that this is the reverse jump. And if the reverse jump happens, then what will be the angle between E to X and X to A is simply 180 degree, and therefore in that case cos theta I plus 1 will be equal to minus 1. Remember again, cos theta I and I plus 1 simply denotes the angle between the ith jump vector and I plus 1th jump vector. So the first vector here was from E to X, okay, and the second vector, that possibility that we have written, this was our initial ith jump, and this was one of the possibilities of I plus 1th jump. So you see that the angle between these two vectors is 180 degree, and therefore the cos theta I plus 1 is written as minus 1. The second possibility is that it can jump from X to B. That will be a forward jump. So if your ith jump is this and X to B is this, then the cos theta I plus 1, the angle will be actually 0 degree, and therefore the cos theta is equal to plus 1. Now, in any of the other four directions, that C, F, D, E, all are equivalent, and they are the 90 degrees to the ith jump vector. Okay. So, that angle, so this angle, ith jump, and let's say here you can clearly see, here you can see in all the directions, C, D, E, F, the jump vector is perpendicular to the ith jump. So, therefore, the cos theta I plus 1 for this type of jump will be equal to 0. So, the tracer can make, or the atom can make the reverse jump, then the cos theta I plus 1 will be equal to minus 1. It can make a forward jump, where in which case cos theta I plus 1 will be equal to plus 1. Or it can make a jump to any of these four sides, in which case it will be a perpendicular jump. So cos theta I plus 1 will be equal to 0. Now remember, this is for one atom. Okay. Now, suppose because our task is to evaluate this average for jumps of n number of atoms. Okay. Therefore, I am repeatedly saying that we are evaluating average for n number of atoms. So now let's say out of n atoms, okay, n1 atom makes the reverse jump. Okay, n1 atoms make reverse jump, n2 atoms make forward jump, and n3 atoms make perpendicular jumps. Okay. Now what we can write then, the average of cos theta I plus 1 is nothing but n1 times minus 1. That means n1 atoms have made reverse jump. So multiplied by the cos theta I plus 1 in that case is minus 1, plus n2 times plus 1 plus n3 times 0 divided by total number of atoms. So, this one term will go out, and we will have n2 by n minus n1 by n. Now, what is n2 by n? n2 by n, n2 is the number of atoms made which made forward jump. n1 is the number of atoms that made the reverse jump. So, n2 by n represents a probability of a reverse jump. Similarly, n2 by n represents the probability of forward jump, and n1 by n represents the probability of reverse jump. So, we can write n1 by n as PR and n2 by n as PF. So, therefore, the cos theta I plus 1 average can be written as PF minus PA. Let us call this as equation 1. Now, what about how do we consider I and I plus second jump? To consider the combination of ith and I plus 2 jump, we also need to consider ith, I plus 1 and I plus 2 jump sequences. In this case, we will not consider perpendicular jumps because we know that the cos theta for them will be equal to 0. So now what are the possibilities? Again, let us draw this figure. Let's say we saw in the previous slide, ith jump has happened from A to X. So A to X. Now we saw three cases, remember? For the I plus 1th jump, it can be either a reverse jump, a forward jump, or a perpendicular jump. But perpendicular jump, the cos theta will be 0, so we are not considering that. We are only considering the case of when the I plus 1th jump is either forward or reverse. So, if let's say I plus 1th jump is from X to B. So, X to B. In that case, the probability of this forward jump is how much? PF. That is what we saw in the previous slide. Now, after the atom has gone and made the jump in a forward direction, now where will be the I plus 2 jump? Now, again, there are two possibilities. That I plus 2 jump can be forward, which is will be in somewhere here. Then the probability of that jump will be PF. Then the case 2 is that I plus 2 jump can be reversed. That means it can come back to X, and the probability of such a jump will be PR. So you know that when you have two jumps, so like that, like if you have a bag full of red and black balls, and if you want to find out the probability when you take first ball is red, second ball is black, then you multiply the probabilities, right? Similarly, when now you have to say that, okay, ith jump was from A to X. What is the probability my I plus 1th jump is from X to B? It is here. Now, what will be the probability that I have a forward jump as I plus 2? So I have to multiply that probability. Similarly, what is the probability that I plus 2th jump can be reversed? Okay, the total probability. So when I am considering the total probability, the it is equal to PF into PF, that is equal to PF square. So therefore, the cos theta I plus 2 in this case will be plus 1. Remember, for PF it is 1. For this PF also it is 1. So therefore, the multiplication will give us plus 1. Whereas PF into PR, here PR will have negative cos theta. So therefore, cos theta I plus 2 will be minus 1. Moving ahead, this is, remember the here in this case, we have only considered one case of I plus 1th jump, which was forward jump. But I plus 1th jump can be reverse also. So let us consider that probability as well. So if the ith jump was from A to X and I plus 1th jump was from X to A, which is the probability PR, in that case, the I plus second jump can be forward, and then it will be equal to the total probability will be equal to PF. Whereas here, the also the possibility is that I plus 2 jump can be reversed, and in that case, the total probability will be PR. Only for I plus 2th jump, it will be PR. The total probability, when we calculate, it will be PR into PF if you have a case 3. So then you get cos theta I plus 2 as minus 1. Whereas for the case 4, if both the jumps are reversed, then it is PR square, again cos theta I plus 2 will be plus 1. Now, therefore, the average of cos theta I plus 2 over all atoms, because there will be some where ith jump is e to x, and then the I plus 2, I plus 1 jump is from X to B, and I plus 2 jump is again in the forward direction. So there will be some number of atoms which will follow this jump sequence. There will be some atoms which will follow the jump sequence denoted by this probability. There will be some which will follow this. So the overall average of cos theta I plus 2 will be equal to PF square minus PF into PR minus PF into PR plus PR square. So this is nothing but PF square minus 2PF into PR plus PR square. So the average of cos theta I plus 2 is equal to PF minus PR whole square. Now, if you recollect from the equation 1, we have PF minus PR was nothing but cos theta I plus 1. So therefore, you have average of cos theta I plus 2 is equal to average of cos theta I plus 1 to whole square. And following the similar extension, we can show that cos theta I plus j is equal to cos theta I plus 1 to the power of j. And although we have demonstrated this for simple cubic lattice, this holds for any cubic lattice. How do we use that now? That particular relation that we derived in the previous slide. So, we know that we have written previously that f is equal to 1 plus 2 by n. And inside the summation, we open one summation here. So, we write cos theta I plus 1 plus cos theta I plus 2 now can be replaced as I plus 1 whole square. Similarly, you can write cos theta I plus 1 whole cube and so on. Now, cos theta I plus 1 can be taken out as common. So, it will have 1 plus cos theta I plus 1 plus cos theta I plus 1 whole square and so on. And this is a summation, a geometric mean. So, geometric series. So, the summation can be written as 1 over 1 minus cos theta I plus 1. Let us call this cos theta I plus 1 average is equal to C. So, we can write F is equal to 1 plus 2 by n times C summation I equal to 1 to n minus 1 by 1 minus C. Now, what happens is if n is infinity, or in other words, if n is very, very large, then C becomes essentially independent of I. That means this average of cos theta I in some sense will not depend upon, it will be independent of whether you are considering, let's say, 45th and 46th jump, or you are considering 100th and 101th jump, or you are considering 10,000 and 10,001th jump. So it becomes independent of I. Okay. So the average of cos theta I plus 1 equal to C, it becomes independent of I as n approaches infinity. So, therefore, you can write f is equal to 1 plus 2 by n. Since this is independent of I, you can simply write it as n minus 1 times 1 by 1 minus c. We can rearrange this as f equal to 1 plus 2c by 1 minus c in the bracket 1 minus 1 by n. Now, as n tends to infinity, so this term will go to 0, and therefore, you will have f equal to 1 plus 2c by 1 minus c. And if you take it here, you can rearrange and write f is equal to 1 plus c by 1 minus c, where c is the average of cos theta I plus 1. So this holds for any cubic lattice, and this holds for diffusion by vacancy mechanism. Okay. So now, remember, till now we are only talking about the correlation factor in a pure metal, and we have not talked about the solutes so far. And now you may ask, what will be the difference in a solute? See, solute vacancy, we have seen that when we talked about the structure and the defect, that creation of vacancy in an alloy, or when a solute vacancy is different from the solvent vacancy, the formation energies are different. Okay. So, therefore, the correlation factors also can be different. In this lecture, we'll only talk about the solute correlation factor. Let's say for the FCC structure. Now, because now when you have a vacant site in inside an alloy, let's say it's a solute vacancy, it has different interactions with the neighboring atoms, because not all the neighboring atoms, the interactions will be similar. So you have, you can see here, this is FCC structure represented here, one of the planes in 2 dimensions. This is a vacancy, and here are the various interactions that are represented. Now, what are these? So this is actually called as a 5-frequency model, and here it's a corresponding energy landscape for diffusion in dilute FCC alloys through vacancy mechanisms. And you see here it is written omega 3, omega 2, omega 1, omega. What are these? Let us see. Omega 2 is the solute vacancy exchange rate. That means how how much is the solute and how at what rate solute and atom vacancies are exchanging the position. This is the solute vacancy exchange rate. Then omega 1 is the rotation rate of the solute vacancy pair. Okay, so this is how this pair rotates is what is given by omega 1. Okay, so for example, if the vacancy comes here, okay, what is meant by rotation? That means the vacancy is exchanging the position with this atom here, which is the neighbor of solute. So therefore, it would look like as if the this pair has rotated. So that rate is called as omega 1. Similarly, omega 3, if you see dissociation rate of the solute vacancy pair. Why it is called dissociation? Omega 3 is here. That means the vacancy exchanges its position by this atom or by this atom or by this atom, which will take it farther from the solute atom. Then the vacancy solute pair will no longer exist. This is called as the omega 3 dissociation rate of the solute vacancy pair. Omega 4. So, for example, after omega 4 is nothing but it is the association rate of the solute vacancy pair. So, for example, a vacancy is lying a little far from the solute, and now it comes in a position where it forms a pair with the solute atom. This is called the association rate of the solute vacancy pair. So, this vacancy was here where it was surrounded by all the matrix atoms. It makes an exchange with this atom here. Now, the solute vacancy pair will be created. This is called as the omega 4. This will also be true for when the exchange happens with this atom. Omega is the vacancy atom exchange rate in the solvent itself. So, for example, here you see that omega, here this is also omega, this is also omega. That means vacancy is exchanging its position with the solvent atom or the matrix atom, which is far away from the solute. So, this is called as the omega. So, this was the 5-frequency model that was proposed, and based on that, the correlation factor expressions were written down or derived. Okay. So, omega 3 by omega 4 is written as exponential minus delta GB by KBT, where delta GB represents the binding energy. Now, suppose a first solute vacancy exchange has occurred. So, the crude approximation, immediate reversal of the first term. That means once this exchange has occurred, the approximation is that it will be immediately reversed. The probability of reverse jump is written as omega 2 divided by omega 2 plus 4 omega 1 plus 7 omega 3, because vacancy can perform 1 omega 2 jump, 4 omega 1 jumps, and 7 omega 3 jumps. Remember, 1 plus 4, 5 plus 7, 12 is the total coordination number for FCC. Okay. So, omega 2, if you see, omega 2 is the exchange with the solute. So, there is only one possibility for omega 2. Whereas omega 3, there are other possibilities. There are total 7 possibilities for omega 3. Remember, this is only a 2D representation. You also have the atom sitting at the top and the bottom. So, the correlation factor, the approximate expression is written as 2 omega 1 plus 7 omega 3 by 2 divided by omega 2 plus 2 omega 1 plus 7 omega 3 by 2. The exact expression also involves an inclusion of a factor F3, which is known as the escape probability. It is a probability that after a dissociation jump omega 3, vacancy will not return to a neighbor site of the solute. See, once the vacancy is exchanged its position, let's say here, it can keep on going here and never return to the near to the solute. So that probability also has to be taken into account to derive the exact expression for the correlation factor. So that correlation factor is given by this expression where F3 denotes the escape probability. In the BCC solvents, you will notice that there is only four frequency model in the dilute BCC alloys when the diffusion is happening through the diffusion mechanism. Because here no lattice size which are simultaneously nearest neighbors to both solute and the vacancy of a solute vacancy here. I leave it as a take home exercise or an activity for you to actually prove that in this FCC case the rotation term was there because simultaneously there were lattice sites which are nearest neighbor to both solute and the vacancy. Whereas here in the BCC structure, that is not possible. So try it for yourself that why only four frequencies are required in the case of BCC. So in this case, the correlation factor is written as 7 times omega 3 into F3 divided by 2 omega 2 plus 7 omega 3 into F3. Remember, F3 is the escape probability. So, with this, we will end our discussion on the correlation factor. And in the next lecture, we'll talk more about the temperature and the pressure effects on the diffusion.